Assalamu alaikum. Let's start with the problems related to moment of inertia of a body. Okay, so here we have a problem, and in this problem, they have defined as that the pendulum consists of a slender rod. You have this pendulum, which is consisting of a slender rod OA, which has a mass per unit length of 3 kilograms per meter. The thin disc has a mass per unit area of 12 k per meter square. This is wrongly written. It will be 12 kg per meter square if we are not mistaken. You can write it over here as it will be 12. This is not k. It is basically kg. It is 12 kg per meter square. Determine the distance y bar to the center of mass g of the pendulum. Then calculate the moment of inertia of the pendulum about an axis perpendicular to the page and passing through the point G. Okay. Now, in problems like this, since he is saying that if you look at in all these problems, you have to make first understand the logic. This logic is that these questions are related to moment of inertia, and you know what is the formula for moment of inertia is. It is basically kilograms meters square. Okay, so basically it will be concerned with the mass, and they have basically given you mass not directly, but they have given you mass as 3 kilograms as mass per unit length. So if you look at it, they have given you as mass as basically 3 kilograms per meter. So as mass per unit length is defined. The thin disc has a mass per unit area of 12 kg per meter square. So, and you first of all need to, he's asking you to calculate he's asking you to calculate this y bar, and he has defined you this point is the origin. Okay, and from here to here you have to calculate the point at G. It will be the y bar. This y bar will be for the entire pendulum. Okay, if this y bar will be for the entire pendulum. This is very important point. Okay, you must remember it will be for the entire pendulum. So some important points that will help you to understand the problem more better. The moment of inertia is always calculated for a volume, and therefore the given figure represents now this whole figure is basically the composite volume. Okay, so this is a very important point that you have to understand that it is a composite. This is a composite volume. Okay, very important point. Apart from that, what is he trying to tell you here is that the center of mass of the individual volumes is off set from the axis. Now he is saying that the center of mass, it is basically offset from the axis that is passing through point G, which means that if you look at it, this rod, this slender rod, its centroid will be somewhere, and its centroid and center of mass will be at acting at approximately this point. Okay, it will be acting at this point. If you want, we can make it as red also, just to understand it. It will be acting at, this is the point. Okay, and basically this is the approximately this point will be 1.5 half of 1.5, and then with this point of the cylinder rod is eccentric from this point. It is eccentric from the point G, and this disc, if you look at it, this disc has basically the centroid of the disc will lie at this point. Okay, and again it is eccentric. If this is the centroid, so it is eccentric from this point G. It is eccentric from point G. Okay, so when it is being eccentric, this means that in order to calculate the moment of inertia, what is trying to say, in order to calculate the moment of inertia for the whole composite volume, we need to use the parallel axis theorem. So why we need to use the parallel axis theorem? Because the overall centroid y bar acting at point G is at a different orientation compared to the centroidal coordinates, and the center of mass of the coordinates is basically at 0.75, and the disk basically center of mass will also be acting at the center of this disk is this point. None of the points are lying at the point G, which is the basically the centroid of the which is basically the center of mass of G of the entire pendulum, this point G. Okay. So you must remember this point. And the concept of Boolean algebra in case of moment of inertia can only be used if the center of mass of individual volumes coincides with the center of mass of the composite volumes. Okay, so what does it mean? If the center, he is saying you can only use the Boolean algebra if the center of mass of the individual volumes, okay, which there, how many individual volumes are there? This is the individual volume, which is, this is a cylinder rod, and then this is the disc. If they are basically the center of mass of these discs must be lying on this point G, then you can use direct the Boolean algebra. Otherwise, you cannot use it. This is a very important point. Now, first of all, in our first and primemost target is basically this point Y. This point, this Y needs to be calculated. So, what will be the formula to calculate Y bar, which is basically the center of mass G of the pendulum? So, to calculate the center of mass of the whole pendulum, we give it a symbol of Ym. Okay. So it will be summation of y tilde m times the mass divided by summation of all the masses. So what does it mean? The numerator means that you have to calculate y tilde m multiply, and this is the mass. Okay, what is this? This is the this is mass, but it has to be in kg. It has to be kg. They have given us n kg per meter. Okay, so you have to calculate y tilde m for, basically you have to calculate y tilde m for the cylinder rod, and you have to calculate y tilde m for this disc. Okay, and remember there is also in this disc is not solid, it is all hollow also. So this is a very important point to be under consideration, because this disc is not solid, it is basically hollow. So here we will be using some very key points, and that key points is that since it is hollow, we will assume to basically consider this disc as fully solid. We will consider this disc as fully solid, and there is no hollowness over here, and then from this solid disc we will subtract basically what is called as this hollow area from this disc to make it exactly the way it is in the pendulum. So as we have done in one of the previous problems of our basically we did in the area problems and the volume problems. Okay. So the reference point we have is O. So how shall we proceed with this? We have, this is the formula. So we need to calculate the y tilde m for the thin rod. Then we also need to calculate y tilde m for the for this disc, hollow disc, but we'll assume it as a whole solid. And then we'll subtract this hollow area from this whole solid disc to match it out with the actual geometry given in the numerical. So how shall we proceed now? It is very simple. As according to this formula, y tilde m into m, we are given basically the mass number 1. Number 1 is, if you look at the diagram, this is number 1. This is the center rod. But they have given us that the mass per unit length of the cylinder rod from O is 3 kilograms per meter. Okay. So what does we need? Basically mass in kg. So what we can do here is that this we can do is that 3 kilograms per meter multiply by 1.5 meter. So this meter and this meter are cancelled and we get the value as 4.5. Okay, so we get this value as 4.5. And what will be the centroid, the local centroid y tilde m for this whole cylinder rod, which is 1.5 meter? It will be 0.75 meter. It is 0.75, 1.5 divided by 2. Okay, now we come to this disc. Okay, but again we are assuming that this disc, basically number 2 is made up of first number 2 is treating it as a solid disc, and 3 is treating it as a hollow part that needs to be subtracted. Okay, so if you look at it, we can to be understanding it, just assume that this disc is basically all solid. There is no hole into it. Okay, this is all solid. Okay, and this is basically what we call it as number 2. And number 3, which is, we will assume that it is hollow. This is number 3, it is hollow. Okay, so from number 2, if we subtract this part, we will get this actual geometry. Very important point. Okay, so once this point is understood, how shall we proceed now? So the mass given to us for the disc, thin disc, is basically 12 kilograms per meter square. So it is basically 12 kilograms per meter square. So if you look at it, 12 kilograms per meter square multiply by pi, and what will be the radius? Is basically 0.3 square, 0.3 square. Okay, so and this, since it is area, this will be meter square. So what will happen to this meter square cancels out with this meter square, and you multiply 12 kg with pi and with 0.3 square, you will end up with this result. Okay, so this is what it is. Again, if you 12 multiply by pi multiply by 0.3 square. Okay, so this is how you will get this value, 3.392. And what about this one? So we assume this was, number 2 was the whole solid disc, and number 3 is basically, we assume it is basically a hollow disc. So again, for hollow disc also we can write, he has given as 12. Again we write 12 kilograms per meter square multiply by multiply by pi into 0.1 the whole square. Okay, 12 kilograms per meter square into pi r square, meter square gets cancelled, and we end up with this result. But again, very important point is here is that here we are going to use a negative sign, because we considered 2 as a whole solid thin disc. So we subtract number 3 as we say as a circular cutout. So we basically get up this result minus 0.376 after multiplying this. And again, if you look at it, what will be basically the centroidal local centroid of the this disk? Okay, what will be the they say it is 1.8. It is 1.8 for number 2, and because if you start from here, what was ym equals to, what was basically from here to here, the distance is given as 1.5, and if you look, the centroid will be at, that since the radius is 0.3, so from here to here the centroid will be at 0.3, so 1.5, so it will be 1.5 plus 0.3 from the origin, from where, from this point, from the origin, so it becomes 1.8. So now what you will do, very simple, you will just be multiplying, because the formula says y tilde into m, you multiply y tilde into m, you get this value, you get again y tilde for number 2, for the solid disk full 1.8 into 3.392, you get this value, you multiply this 1.8 with 0.376 with a negative sign, so you get this value but with a negative sign. So now what you will do, as from the formula, you will add all those y tilde into m's, and this comes out to be 8.8038, and you will also add all those masses, okay, and you will get this value 7.516. so in the numerator we have this, in the denominator we have this for the formula, and we get ym equals to 1.1713. okay, so we have got this ym as 1.1713. okay, this is comes out to be 1.1713. so very important point of usage. If you look at it, this is very important. Okay, just this is 1.1713. okay, so this is ym 1.1713, always remember, and this is the y bar m for the whole pendulum. okay, now we basically go and proceed to calculate what he said is to calculate y bar has been calculated, the moment of inertia of the pendulum about the axis perpendicular to the page through G. okay, so he is asking you to calculate the moment of inertia of the whole pendulum about which axis is he trying to say? He is trying to say this axis, about, if you look at, this is the axis which is perpendicular to the page, it is coming out of your screen. okay, he is talking about the moment of inertia of the pendulum about an axis which is perpendicular to the page and passing through point G. This, you see it is an angle, but actually he is trying to say it is coming out of the screen, since it is perpendicular to this xy plane of the pendulum. okay, so this is what he is trying to say. So how shall we proceed now? We need to calculate, if the figure is there, we need to calculate the moment of inertia for the basically rod individually, the moment of inertia for the rod and the moment of inertia for the disc, before calculating the entire moment of inertia which is perpendicular to this point, perpendicular along the perpendicular axis passing to the point G. okay, so basically again the gives the we have here very important that you have new formulas coming. The moment of inertia, okay, the moment of inertia of the thin rod. okay, what is he saying? The moment of inertia of this thin rod here since it is given as 1 by 12 ml square. It is given as 1 by 12 ml square. You have to learn it, okay, or memorize it. And the moment of inertia for the disk, 1 by 2 mr square. For this, whether it's a solid disk or hollow disk, both of them, it will be given as 1 by 2 mr square. You have to memorize it, and you have to memorize this, okay, because these are the moment of inertia for the thin rod and for the disk, okay. If it is even rod, you can also write it as thin, THIN, for the thin rod, okay, for the thin rod and for the disk. Okay, so above formulas give the moment of inertia of the rod and disk about the axis perpendicular and through the center of the mass. Okay, this is very important. So the first, basically, as we have told you, since the center of mass of the thin rod is basically at this point at the center, and for the disk it is acting at the center of this point, so they are not at point G. So we need to use the parallel axis theorem. Okay, it is saying the moment of inertia of the rod and disk about the axis perpendicular and through the center of the mass, so using the parallel axis theorem. So for the rod, how to use the parallel axis theorem for the rod? Okay, so again we will simply say that the moment of inertia, we will simply say that we will say the moment of inertia of the disk about an axis perpendicular to the plane of the rod and passing through point G is given by Ig1, which will be equals to I center of mass for the rod 1. Okay, which means this is going to be this point. Okay, this point, and again okay, this is going to be your ICM1 for the rod, and again you have another one after that. When you go, this will be another point, or you can basically, if you want, you can use this also here. Okay, this will be your what? This will be your IC2, ICM. It will be your ICM2, but this will also be equal to, afterward you can ICM3 also. Okay, just these axes you must know. Okay, it will be very easy for the calculation. And where is your ICM? This is your ICM1. Okay, so now how to proceed with this? Basically you will say that the moment of inertia of the rod at point G will be Ig1 for the rod equals to moment of inertia of the center of mass at point 1 of the thin rod plus m1 times d1 square. m1 is the mass, and d1 square. D1 square, again d1 is the how do you calculate d1? This is a very important point. We will calculate d1 because it is this distance. If you look at it, it is this distance. It is this distance. Okay, so it is how much? 1.1713. If you look at it, 1.1713 minus 0.75. Okay, this was one till point it here it was 1.173, and basically from here to the midpoint it is 0.75. So you will get, subtract this distance from this distance, you will get this distance. Okay, so this comes out to be 0.4213. So now you simply apply the formula, and one more thing, this is m1. M1 is the mass. We calculated it as 4.5 kg. This was the mass we calculated as 4.5 kg. If you look at it, this was 4.5 kg. So you put all the values here. Ig1 will be equals to, again, ICM1. What was ICM1? This is basically your ICM1. And where is the formula for IMCM? This is 1 by 12 ml square. So 1 by 12 m is the mass, L is basically a total length, 1.5 of the rod, plus what is the mass, 4.5, and what was D1, 0.4213 square as according to the formula. So what you will get here is that Ig1 is 1.64175. Since this is moment of inertia, it becomes, it is mr square kg meter square. So this is done. In the same logic, applying the same logic for this solid disc, which is actually number 2. Remember, number 2 is solid and number 3 is the hollow. Okay, when we say solid, we assume there is no hollowness in it. So again, Ig2 basically for basically the moment of inertia, it is the moment of inertia of the solid disc basically acting at the point 2. Okay, it will be, and again this moment of inertia of this solid disc which is at point 2, this is we are going to treat it as, so the moment of inertia of the disc about the axis perpendicular to the plane of the disc and passing through the point G, okay, is equals to ICM2. ICM2 is again the moment of inertia of this solid disc which is acting at this point 2. This is ICM at point 2, and Ig2 is again the moment of inertia of the disc about an axis which is perpendicular to plane of disc and passing through this point G. Okay, so this is what he is trying to say. Ig2 equals to ICM2 plus m2 into dt square. So ICM2 is what? What is ICM2? ICM2 is already being defined to as this. This is ICM2. So again, and what was m2? M2 was given to us as, for the whole solid disc, as 3.392. We calculated it. And what was D2? D2 was again, from the origin we do all the calculation, 1.5 plus this radius 0.3. So this was basically again, if you look at it, your D2 will be, you already know what your D1 was. This was your D1, and if you look at it, this will be your, this distance will be your basically this distance will be your D2. And basically, how have you calculated this distance? You have calculated this distance from here to here. It is how much? 1.8. This was how much? 1.8. 1.8. This was how much? 1.8. And you minus this distance from here to here, which was ym, and ym was how much? It was basically given to us as 1.1713. This was ym, 1.1713. So if you subtract this, you will get this distance. So I hope you understand it. Now you put all those values. 1 by 2, 3.392 into 0.3 was the radius. It was the radius r square, or this was radius, this 0.3 square plus what was mass m2, 3.392, and d2 you calculated as, here you calculate 0.6287 the whole square. So you will get Ig2 as 1.4933 kg per meter square. And then you here in number 2 you say the disk is solid. You say the disk was solid. Okay, and then in here you subtract the inner circle. So here you subtract number 3. Okay, so here you basically, what you do, you subtract this thing. If you look at it here, from this solid disk that you assume, you subtract this. Okay, you subtract this inner hollowness, which is number 3, defined as a circle of pi r square, which is pi into 0.1 square. Okay, so Ig3 equals to Icn3 plus m3d3 the whole square. So d3 basically will be the same as d2 because they both have the same center point. They both have the same center of mass acting at this point. So d3 remains exactly the same, and then half. The only thing is for the formula mass is 0.376, and if you look at it, this 0.376, how have you calculated this 0.376? It was here, remember, you have calculated this as 0.376. okay, so you put it half 0.376 and 0.1 the whole square. We have this thing comes from this formula, which is 1 by 2 mr square. Okay, 1 by 2 mr square plus m3, you calculated it 0.376, and what was d3, 0.6287 the whole square. You basically simply simplify this and you get 0.1504 kg meter square. Now basically, as you told, you need to calculate the moment of inertia of the disk about the axis which is perpendicular to the plane of the disk and passing through point G, so which is this point. Okay, so it will be, so of the whole pendulum, since it will be Ig1 plus Ig2, and not plus here, but here very important, it will be minus, because remember this Ig2 was whole solid and this Ig3 was hollow, to get exactly the same profile which is given in the figure. So you minus this. So your total your moment of inertia of the disk about the axis perpendicular to the plane of disk and passing through G is basically this Ig. This is your Ig. So it's a very typical problem, and basically if you understand, I try to understand, let you understand the basic fundamental concepts of solving this problem. So we finish this problem, and with this also we finish the chapter 10. Okay, so I hope you have understood this very important chapter. Thank you very much. See you, and we'll start in the friction chapter. Okay.